So let me use this initial value problem to see how this amazing idea works. So here's a typical second order differential equation with a constant coefficient, and there I put some initial condition y0 and y prime 0 both being 1. So you turn that into this differential operator notation. So you separated the action and the function, and because it's a constant coefficient, we can factor that operator algebra like this. So wrote it down here, and we're going to turn this to the second order differential equation to a first order differential equation. See that if I substitute this entire thing here with z, so if you apply y to this d minus I, that's y prime minus y. If I call that function z, this equation becomes a first order linear differential equation. Z is in here, that whole thing is replaced by z, and d plus 2i is the first order operator. So z being like, once you solve this thing for that z, and you can come back in and solve for y here again, this is going to give you another first order equation. Before we focus on this first order equation on z, we need an initial condition on that one. So at 0, both derivatives are, both the function value is 1, and derivative is 1 here. So it's 1 minus 1 is going to be 0. So here we're looking at z0 equals 0. Alright? So it's the first order equation with this initial condition. So what I'm doing down here is I turn this one as the first order equation, z prime plus 2z, and figure out integrating factor of this linear first order equation and go through the method, typical method. And I'm concluding down here, as you can see, z is c times e to the negative 2x. And because of this initial condition, and the c has to be 0. If this constant c has to be 0, then the function is the 0 function. So this easy way to do this one, if it is a linear equation, if you have an initial condition like this 0, and the 0 function is obviously the answer. Here's 0 differentiated 0, and 2 times 0 is 0. Right? Initial condition like this in a first order, because of the uniqueness and existence theorem, the 0 constant function works. This initial condition is the solution. Anyway, now the z is a constant function 0. So you go back here and put that 0, the constant function, and solve this one, and considering this initial condition for y. Now, to remember this part, originally that was a second order differential equation, but we factored it and absorbed that one of the factor into this function part z, which is described it here. That was d minus I. So we now solve this. The only thing that satisfied this condition here is a 0 function. So that condition and this differential first order differential equation is a 0 function, a constant function. You set that one equal to 0. That connects to y prime minus y equals identically 0. With this initial condition, y0 equals 1. We don't need that y prime of 0 equals 1 here. It's a first order, and this initial condition will be sufficient to conclude there's a one and only one function that satisfies this condition. Okay, but we use that y prime of 0 to calculate the initial condition of function 0, z of 0 here. We use the value y prime 0 as 1. So the rest of the part is first order linear differential equation with even constant coefficients. It's a typical integrating factor, and at the end we conclude as y equals e to the x. Here's our problem again. This is a second order linear differential equation with a constant coefficient, and we were able to factor this operator expression because it's a constant coefficient. It's easy to factor. Then we can deal with a linear operator, first order operator at a time. We're able to conclude that the only function that satisfied this initial condition and the second order differential equation here is e to the x. And existence and uniqueness theorem says there's only one function, and we found that function to be y equals e to the x.